Okay, so here is our clock. Let's imagine that we've got an astronaut, and here he is in his stationary rocket ship. Stationary, well, obviously, stationary with respect to the astronaut anyways, so the astronaut thinks that the rocket is stationary. And here's the astronaut's clock, and this clock is made of, let's say, two parts, or, well, several parts. We have a little emitter here that emits a beam of light. That beam of light then goes up to a mirror or reflector. It is then reflected down, and it is received by a receiver. And as soon as the receiver receives the beam of light, another one is sent up here, reflected down. And so here's our clock. You might think tick, tock, like that. And as it, for every tick, we can imagine our clock ticking 1 second or something like that, progressing along. Let's imagine that the distance between our two the emitter and the receiver and the reflecting surface, let's imagine that is some distance, big D. And let's imagine that the time between the ticks, so tick, tock, and then the next tick and tock, let's call that some time interval. We'll call that delta T naught. Now, this is very, very important. Delta T naught is the time as measured by the single clock, or on one clock. So this clock, that is stationary with respect to the astronaut in the rocket ship, that is measuring the time delta T naught. We will refer to this time as the proper time. So the proper time is the time between, the time as measured on one clock. And it's the time difference between two events. The two events being the emission of the light and the reception of the light. So those are the two events. The emission, tick, tock, the emission being one event, the reception being another event. The time interval as measured by the astronaut is then measured on the one clock, and that we will refer to as the proper time, and we will write it as delta T naught. Now, let's imagine that the rocket ship is moving relative to the Earth, or we could say the Earth is moving relative to the rocket ship, one way or the other, but let's look at that motion from the perspective of the Earth's reference frame. So here we go. Here's the rocket. Now moving to the right relative to the Earth, or the Earth is moving to the left relative to the rocket. Here are the two events. The event here, the emission of the light. But as the light moves up to the reflector, because the rocket is moving relative to the Earth, the reflector is moving relative to the Earth, and so the pathway that the light actually has to take to go from the event here where the light is emitted by the emitter to the point where it's reflected, the light then travels along this path here up to the reflector, and then needs to reflect back down to the detector back over here. So here's our second event. So first event over here, second event over here. And what we want to do is figure out how much time does it take between those two events when it's measured by an observer on the Earth. We'll call that time delta T. Now, there's a problem with this diagram, and I want to emphasize that. The problem is, for the observer on the Earth to measure the time between these two events, the observer on the Earth will actually need two clocks. One clock over here to measure the time of the initial event, and then one clock over here to measure the time for the final event. So the observer on the Earth cannot do this with a single clock. She will have to have one over here, a clock over here, a clock over there. She will need two different clocks. Now you might say, well, that's kind of silly. Why can't she use a single clock? Well, to use a single clock, we would have to wait for the light to travel from one event over to here. We'd have to wait for the light to travel from one event over here, trying to make sure that those events actually correspond to, or the amount of time that light would have to travel is a little difficult to say, because we need to make sure that she would be at a central point between those two events that are occurring at different times, and we've already seen that in different frames of reference, where a point is, the distance between two things can depend on the reference frame and how that reference frame is moving. So that creates a little ambiguity that we can remove if this person, the observer on the Earth, just uses two different clocks. So she will have one clock over here, another clock over here, both of which are stationary with respect to her. In other words, they are in her reference frame. All she has to do is make sure that those two clocks are synchronized with each other. In other words, they are reading the same time. Okay? And as long as that is true, she can use one clock over here to measure the time of this event, another clock over here to measure the time of this event. Now we have a very, very important asymmetry between these two measurements. The time difference between the two events is measured by a single clock for the astronaut, two clocks for the observer on the Earth. So, remember, if the time interval is measured by a single clock, that's the proper time. She is measuring the time interval with two clocks, so that is not the proper time. We will call her time delta t. So we'll assume that the amount of time that she determines to be the difference between these two clocks, we'll call that delta t. Now, is there a relationship between delta t and delta t naught? Well, let's think about that. Let's go back to our first picture here. We know that this path is being covered by light, and we know that light travels at the speed of light, c. So the time interval, delta t naught, the amount of time that the light has to travel from here to here to here. In other words, to travel a distance of 2d, the light needs an amount of time delta t naught. So just using a simple result, distance equals speed times time, we have that 2d equals c times delta t naught. So the distance traveled by the light, 2d, is equal to the speed c times the time delta t naught. Now, let's look at what's going on the Earth. Here we go. Now, in this case, light is traveling along this distance s. Say from here to here, we'll call that distance s, and then likewise another distance s back down here. So the light in the frame of reference of the observer on the Earth is traveling a distance of 2s in a time delta t. So again, we could write that 2s equals c delta t. However, let's look at the rocket. The rocket, we know, is moving at a speed v. And the rocket moves a distance of L and then another distance L in time delta t. So the rocket moves a distance of 2L in a time delta t, and the rocket is moving at a speed v. So we have that 2L is equal to v delta t. All right, there we go. So we got these three results, three distances. Two of them traveled by light, one of them traveled by the rocket. And now let's look at this triangle right here. We have a length of this leg of the triangle of L. This leg is D. The hypotenuse is S. So we have that S squared is equal to L squared plus D squared. Okay? There we go. Now, we'll take the picture off. I can actually turn this off. Oh, good, thanks. All right, so now we've got this picture here. Actually, let's just get rid of the triangle. We don't need the triangle anymore. And what do we have? We have that S is c over 2 times delta t. So we have c over 2 times delta t. And we need s squared. That equals L squared. But what's L? L is V over 2 delta T squared plus D squared, and D is C over 2 delta T naught squared. Okay, well, let's square these and see what we get. This gives us C squared delta T squared over 2 squared, which is 4, equals V squared delta T squared over 2 squared, which is 4, plus C squared delta T naught squared over 2 squared, which is 4. We can multiply the whole equation by 4 and get rid of all of the 4's in the denominator. And there we go. Let's bring this term over here. We'll write this as C squared minus V squared times delta T squared equals C squared delta T naught squared. Let's divide both sides by a C squared. So we'll have C squared over C squared, that's 1, minus V squared over C squared times delta T squared, which is equal to delta T naught squared. Let's divide both sides by this quantity here. So we'll have delta T squared equals delta T naught squared over 1 minus V squared over C squared. And then let's take square root of both sides. So I'll abbreviate this a bit. Take square root, and square root. There we go. What we end up with is this final result. Delta T is equal to 1 over the square root of 1 minus V squared over C squared times delta T naught. Well, first of all, this shows us something very, very interesting. That delta T is not the same as delta T naught. They are different by a factor of this thing here, this thing that looks relatively complicated. Delta T naught is different from delta T by the multiplication of this factor. Well, let's look at this factor in just a little bit more detail. We're going to use that factor, but we're going to simplify its evaluation a little bit. First of all, we're going to evaluate V over C. We know V, that was the speed of the rocket. We're going to take that speed and divide by the speed of light. What this tells us is basically the speed of the rocket in terms of the speed of light. This is what we will call the quantity beta. We call this the relativistic velocity, or the relativistic speed, either one. We're not worrying about directions at this point. So relativistic velocity, relativistic speed. For example, let's imagine that V is, let's pick that speed that I used before. Let's say 1.5 times 10 to the 8th meters per second. What's beta in that case? Well, beta will be V over C, 1.5 times 10 to the 8th meters per second, divided by 3 times 10 to the 8th meters per second. Well, meters per second cancel, 10 to the 8th cancels, 1.5 over 3, that's 0.500. So for this speed, beta is just 0.5. So what that's telling us is that this speed is basically half the speed of light. Beta is just telling us what fraction or what decimal our velocity is relative to the speed of light. So knowing that beta is 0.5 means that the rocket is traveling at 0.5 times the speed of light, or half the speed of light. If this were, let's say, 1.0 times 10 to the 8th meters per second, beta would be 1/3. The rocket would be traveling at 1/3 the speed of light, etc., etc. Okay, so beta tells us the relativistic velocity, the speed of the object relative to the speed of light. Well, using that, we've got V squared over C squared. We can write this thing then as 1 over the square root of 1 minus beta squared. This quantity is what we will call gamma. And gamma is what we will refer to as the relativistic factor. Okay, so that then is gamma. So we can rewrite this equation much more simply, although we still mean exactly the same thing, as delta t is equal to gamma delta t naught. Okay, so what's the bottom line? What's going on here? Well, let's stick some numbers in here and see what we get. Let's imagine that we actually have a speed of, let's say, 1.5 times 10 to the 8th meters per second. We already know that's a value of beta of 0.500. Gamma will be 1 minus 0.5 squared, square root, under 1. So 0.5 squared is 0.25, 1 minus 0.25, 0.45, 0.75. Take the square root of that, take the inverse of that, that turns out to be about 1.15. Let's imagine that the astronaut's clock is ticking once every second. So let's say that delta t naught is 1 second. What this tells us is then that delta t is 1.15 times 1 second, or 1.15 seconds. Oh, sorry, just before we go on, let's notice, what are the units we're talking about here? What are the units of beta? Well, the units of beta will be the units of velocity divided by the units of c. They'll cancel out, so beta is a unitless quantity. Likewise, gamma, which only involves beta, will also be a unitless quantity. So both beta and gamma are unitless. So delta t is 1.15 seconds. Now, what does this mean? If we'll remember, this is the time interval as measured by the astronaut. This is the time interval between the ticking of the clock, of the astronaut's clock, as measured by the observer on the Earth, and that is 1.15 seconds. So the observer on the Earth measures the time interval between the same two events that the astronaut is measuring as 1.15 seconds versus 1.00 seconds. Well, let's imagine that this astronaut, maybe the astronaut's heart is beating once a second, just like the clock. So every time the clock ticks, the astronaut's heart beats. Well, the observer on the Earth will look at the astronaut and it will appear as though the astronaut's heart was beating more slowly. Maybe the astronaut is walking. The observer on the Earth would look at the astronaut and it would look like the astronaut was walking more slowly. Everything that is happening on the rocket, the observer on the Earth would look at and it would appear to be moving more slowly. Time itself would seem to be moving more slowly when viewed by the person on the Earth looking at or observing the astronaut in the rocket ship. This is a very, very strange thing. Why don't we notice this kind of thing? Why don't we notice if a car drives by? Why don't we notice that the person in the car is moving more slowly or aging more slowly or something like that? Well, when we put in this very, very high velocity, we get something that obviously could be noticeable. Let's put in a more reasonable value and see what happens. Let's put in a more normal value, like, say, a walking speed of maybe 1 meter per second. So let's imagine that v is 1 meter per second. What's beta in that case? Well, we'll have 1 meter per second divided by c, 3 times 10 to the 8th meters per second. What do we get in that case? Well, we end up with a value of I want to make sure I don't make any mistakes here, of, this will be minus 8, so 3.33 times 10 to the minus 9, or 0.3 times 10 to the minus 8. We get a very, very small number. Well, what's gamma? Gamma is 1 over 1 minus 3.33 times 10 to the minus 9 squared, square root Well, stick that in your calculator and see what you get. You will get 1.00. Well, to 3 sig figs anyways. As a matter of fact, this is different from 1.00 only by a term of 5.56 times 10 to the minus 18. So, if delta T naught were again 1 second, what would delta T be? It would be 1 second plus 5.56 times 10 to the minus 18 seconds. And so the difference between the time as measured by the observer on the Earth and the time as measured by the observer in the rocket is just 5.56 times 10 to the minus 18th seconds. This is an extremely small amount of time, and it is not something that, or not the rocket, but by the person walking by or whatever. This is such a small time difference that you would never notice that difference. So the bottom line is that the reason that we don't notice these kind of effects in our ordinary everyday lives is that the speeds that we're talking about that go into gamma are much, much smaller than the speed of light. And so beta is a small fraction, small decimal. Gamma is a very, very small difference from 1. And so the difference between the time as measured by say a stationary quote-unquote observer and one moving relative to that observer, the difference between those is going to be very, very small typically. They're going to be very close to being equal to each other. Let's just take a look at what kind of values we're talking about for beta and gamma. So for velocities or for speeds, remember we're talking about anything greater than 0. We're not talking about direction or anything like this. We're just looking at the magnitude. So velocities could be 0 if it's not moving, bigger than 0, or up to values less than the speed of light. The only time that we will ever see anything going at the speed of light will be if we're talking about light itself. Or there are some other kind of waves that actually travel at the speed of light, but essentially for anything with mass, any matter, we're talking about velocities that are going to be less than c, not equal to, but less than c. Beta, then, which is the velocity over c, will have values greater than or equal to 0, and then if v approaches c, beta will approach 1. So beta will have values anywhere from 0 to 1. Now, what about gamma? Let me just write gamma down here again. Gamma is 1 over the square root of 1 minus beta squared. So gamma, when beta is 0, we put in 0 here, 1 minus 0 is 1, root 1 is 1, 1 over 1 is 1. So gamma will have a value of 1 when beta is 0. Now, what happens when beta gets large, in other words, starts approaching 1? Well, we'll have 1 minus a number that's close to 1. As beta increases, 1 minus beta squared will approach 0. It'll get small. We'll take the square root of that. We're talking about another small number. 1 over a small number is a big number. So when beta is 0, gamma will be 1, but as beta approaches 1, gamma gets very large, or we'll just say approaches infinity. So gamma will have values that are greater than or equal to 1, and then up to infinity. It just gets bigger and bigger. As the velocity approaches c, beta will approach 1, gamma will approach infinity. All right, so typically for ordinary everyday type experiences, the velocities are very small, near 0, as compared to c anyways. Beta, very close to 0 or small numbers. Gamma, very close to 1. It's only when we're talking about much, much higher speeds, on the order of the speed of light, beta getting big, near 1, gamma getting very, very large, do we start getting any significant differences that can actually be measured. Now, let me draw your attention to a very, very fun, readable book. If you are interested in this, there is a book called Was Einstein Right? By an individual by the name of Clifford Will. And this book is all about experimental verifications of Einstein's theories. So what kind of experiments have been done to demonstrate the accuracy of these sorts of things, like the fact that delta t is equal to gamma times delta t naught. The fact of the matter is that has been experimentally verified. If you take what has been done was two atomic clocks were synchronized with each other. One was put onto a jet and then flown around, brought back, and once brought back, those clocks no longer were synchronized. The one that was in the plane actually had less time pass on it relative to the clock that stayed on the Earth. So there have been experimental verifications of these ideas of Einstein, and this is a great book if you want to read about them. Was Einstein Right by Clifford M. Will. I personally can vouch for Cliff, just kidding, because Cliff Will was my thesis advisor in graduate school. So I think you can trust him. So anyways, next time we will continue with these ideas of special relativity. We have looked at how the measurement of time is different for two different observers. What about the measurement of length? Now we looked at the simple example that the distance between two events is not the same, obviously, but what about the actual physical length of an object? We'll take a look at that starting next time.